Thanks. So today I'm going to talk about quantitative mapping and tracking of lunar surface hydration with MCube data. As we know, previous studies show the near-infrared reflectance spectra indicated the lunar surface is hydrated. However, both quantitative and qualitative mapping of lunar surface hydration with MCube data are constrained by thermal effects at wavelengths larger than 2 micron, especially at 3 micron bands. This is because the thermal emission appears to be underestimated in current empirical models. We developed a new standard empirical model for MCube data based on the reflectance of Apollo and lunar samples measured at Gray Lab. And also this model has been constrained with independent measurements of surface temperature. Here we use the divine volumetric temperature data, and they are overlapping with the MCube data at the same lunar local time. In the meta part, I'm going to touch a little bit details for the modeling. So our objectives in this study is going to get the quantitative estimates of lunar surface hydration. We're going to use our new thermally corrected MCube data. And then we want to investigate the lunar surface hydration variation with the location, for example, the latitude, the far side and near side. And then with the variation with the local time, for example, from local morning to noon and to the afternoon. And then want to know the variation with the composition, for example, the mine and highline. After that, we want to investigate the hydration variation with the maturity. Here we want to compare our water mapping maps with optical maturity parameter derived from climate data. And then at last we want to know the lunar surface hydration varies with the depth of sources, for example, regolith, crater ejecta, and periclastic deposits. So for the method part, first we investigated the relationship for the reflectance at 1.5 and 2.5 micron bands for both Apollo and lunar samples, including soils, rocks, and glasses. And the black cross shows the data, and the red line, we can see they follow a very good trend, and the red line is the regression line. And after that, we acquired the diviner data, and with the radiative transmodel, and then do the thermal correction for MCube data. We selected several research areas, covers a wide variety of composition, maturity, and albedo. So the blue line is the relationship between the reflectance at 1.5 and 2.5 micron bands for MCube data. So we can see they are almost identical. So then we apply this semi-empirical model to the global MCube data. First, we used the power law to predict the reflectance at 2.5 micron bands without thermal effects, based on the reflectance at 1.5 micron bands. Then the data are converted back to the readings, and all observed excess readings is assumed to be due to thermal emission. Then we can remove the thermal effects. And if there is no, even the predicted readings data is lower than the observed, we are not going to do any correction. So the red bottom plot shows an example of the spectra at my most frequency. Shows how the spectra looks like out of thermal correction. There are two spectral series. One is dark pixel, the other one is bright pixel. So the right line, the black lines are IOF data without any thermal correction. The red lines are reflectance released by MCube team, and compared with the diviner temperature, we can see they are not tracked enough thermal effects. And the blue lines are the reflectance after thermal correction with the diviner data. We can see the 3 micron bands absorption feature pump out after our enough thermal correction. And then we can use this band to estimate the water content on lunar surface. However, as we know, the band depth will be affected by a lot of factors. For example, particle size, porosity, molecular scattering, a lot of other factors. So we need to find a way, effectively, to get the water content. Previous studies by Millikan and Maxar show that HAPK's effective single particle size of absorption thickness has a very good linear relationship with the water content for a wide variety of minerals. For the plot shown here is our lab-made synthetic basaltic glasses. We can see the water content at the y-axis has a linear trend with the aspect function at 2.9 micron bands. However, we are not sure whether the slope is the same for another side. Currently, we are doing similar experiment to get the slope between water content and aspect function. However, in this study, we know the aspect parameter can be used to proxy for water content. And this is a global mosaic of aspect function we derived with our newly thermal corrected and cube data. If we assume the slope between water content and aspect function is 2.5, the purple region is around 100 to 500 ppm water content. For the blue to greenish region is around 500 to 2,000 ppm water content. From this plot, this figure, what we can observe firstly is the water content is dominantly controlled by the latitude. So we do an average along each latitude and then get the, I'm sorry, here is the Apollo one inside to give you a reference. And then we get the plot like this way. So we can see the water content is absolutely dominantly controlled by the latitude. The reason we mask the polar region because, as we know, in the polar region, the M-cube data, the signal-to-noise ratio is low, so we are not confident about the results. We mask them. But I want to mention here, if we show the results for polar region, it will be similar to what the previous talk shown. They will drop at the polar region, but we are not quite sure about that results. And then we want to know the aspect function, the water content compared with the optical maturity. What we've done is to an average along each 30 degrees from equatorial region to polar region. The upper panel shows the north hemisphere, the bottom panel shows the south hemisphere. We can see for the equatorial regions and mid latitudes, the water content and the optical maturity, there is no obvious correlation. But at a high latitude, as here showing 60 to 70 degrees, we can see they show very good correlation. The very strong correlation, so like higher maturity, higher water content. And also, I want to mention here is sounds like the aspect function compared with the maturity for both north hemisphere and south hemisphere, the trend line, the slope of the trend line is almost identical. So if we think about the origin of the hydration on the moon, we have to think about that it's for both north hemisphere and south hemisphere, they are kind of homogeneous. And then we want to know the water content on lunar surface varies with the local time. We find around 1 million pixel overlap from morning to noon and to the afternoon, which is shown in the up left plot. We can see the water content is very high on the morning and it drops at afternoon, and it really increase at noon, at afternoon. But another thing we can observe is like the morning aspect is higher than the afternoon one. And the region covers from around 0 latitude to 55 degree on north hemisphere, around 60. But what we can observe is that at around 50 degree, the trend is not so obvious. And a similar trend has been observed by Sunshine et al. 2009. And also, this is result also consistent with the LEN results. But they didn't observe this phenomena as the latitude beyond around 55, the trend is not so obvious. So this maybe tell us there's maybe some other issue controls the water content, for example, the temperature. And another thing we want to show here is the water content at per cluster deposits, because at a low latitude, for example, from 30 degree to 30 degree, we can see there is no obvious difference between mine and highland, but we do observe some very highly hydrated locations. For example, Aristarchus, Serentatis, and the Humorum. You can see these very high hydrated. And we plot the per class deposits locations, and we can see they consistent very well. So, but some people may argue, for example, there's a highly hydrated maybe due to like morning data. So we have some overlapping data for Serentatis location. We have morning to noon overlapping data. And what we do is do an average within this region along the longitude. And what we observe.
Excuse me a second. You have about 90 seconds left.
Okay, it's almost done. So what we observe here is like this is the per class deposits. The blue dots are the morning data. The red dots are the noon data. What we observe here is around 90% of the pixels exhibit water content drops almost nothing at noon. And however, the per class deposits we can still observe around up to 1,000 ppm water content. This maybe suggests that a large portion of the hydration signature observed for this location may be from volcanic glasses. Maybe this indicate the endogenous sources of the hydration. So for conclusions, lunar surface hydration, the latitude is the primary control for the distribution, and the optical maturity is the second most important factor. And also the lunar surface hydration decreased from morning to the noon and increase at the afternoon for the latitude less than 60 degrees. And also we observe some localized source of increased hydration, for example, the per class deposits. And also the hydration increased with the maturity at a higher latitude, larger than 60, because the latitude is the primary control. And this maybe implies that it needs time to accumulate the water at the higher latitude. And maybe we are not sure whether this is consistent with the slow winter implantation origin, and also this can imply the rates of migration. The highly hydrated per class deposits, we are sure it's not from impacts because it shows strong spatial correlation with the mapped per class deposits locations. And maybe this implies the detection of water bearing glasses, and that's water from lunar interior, as suggested by Sell et al. 2008. And also another possibility is like, is it easier for glasses to preserve hydration formed by solar wind implantation, easier than other materials? Okay, that's it. Thanks.
Okay, so while we're waiting for some of these questions to be finished typing, the next speaker, could they please prepare themselves? Okay, here's one from Indu. Your global SPAT results are derived from M-cubed, but M-cubed data taken during different optical periods. But M-cubed data is taken from different optical periods. The recent photometric correction is optimized for highland materials. Did you consider that?
Yes, yes. Yeah, this is the newest validation, calibration data for M-cube data. What we've done is just data the thermal correction, the new thermal correction.
I guess I actually kind of had a question that was related to this. So you said that you went back to radiance data, right? Did you actually start from a level 1 radiance data, or did you take the level 2 and remove the thermal and the photometric correction?
Oh, but we didn't use level 2 data. We just used level 1 data, radiance data.
Oh, okay.
Yeah.
Mike Poston asks, I didn't catch this, does the SPAT look at water, hydroxyl, or both?
Both. We kind of separated H2 and OH because they are over time at 3 microns, so they overlap.
Okay. I think it's probably time for us to move on to the next speaker. Thank you very